says this is B2, Symmetry and Relativity. Now, I guess I appreciate from the boards that just got raised that Professor Wilkinson just basically dove right into very meaty nuclear physics. So you guys have had a pretty heavy morning, right? Okay. Sorry, I'm not going to liken that. Okay. Yeah, because, even though it's 24 lectures, we got a little, it's still a little bit restricted in time, and I'm sure that you guys want to get into this stuff immediately. Okay, so just, let's see. Oh, okay, click on it. Right, so first just a couple administrative things before we really get started. Now, there is, of course, a Canvas page, and I think I have, oh, change the, okay, anyway. Yeah, so I think, some of this information is actually already on Canvas, and this slide actually is from last year, and I didn't update it. I haven't actually changed a whole lot on the problem sets. Yeah, okay. Books and links. First of all, I guess the main text is something called Relativity Made Relatively Easy by our own Andrew Steen. He was the sort of original lecturer for this course. And yeah, a lot of the material will be drawn from that. I've also drawn a lot from Jackson's classic text, Classical Electrodynamics, which you can probably also find in your libraries. And I've also drawn on a fair number of lecture notes, not only from Andrew Steen, but also Chris Palmer, Stephen Balbus, who of course is going to be doing general relativity next term. So, you can actually kind of look ahead, get to enjoy that. And then, well, I would say that anything written by James Binney is actually worth reading. Yeah, actually drew on that as well. Yeah, so on Canvas, let's see, lecture notes, they are actually being revised after so many years. I mean, I have some old lecture notes that I did from sort of like the first or second year that I actually lectured this course. So of course all the material is kind of out of order, and there's a fair amount of stuff that has dropped off the syllabus. So, that's still on there, kind of for reference, and I have a lot of detailed derivations inside there, partly because it was the documentation of me when I was just, putting all this stuff together. But I'm finally getting around to updating them, revising them, trying to, get the order to be a little bit closer to how we'll actually do that in lecture. So I have weeks 1 and 2 up so far. We'll be updating that as the term goes on. Yeah, I think 1 or 2 of you have already pointed out there are a couple typos in there, which will be corrected. But yeah, if you notice typos, please do send me an email, and I'll try to get that in the next time I update. I also do have some brief lecture notes, kind of like the Cliff Notes version of the course, which is kind of like the stuff that you should have in your head when you take the exams. Okay, so not really so much for now, maybe for later. And then, of course, the problem sets are there as well. Right. Okay. Yeah, we'll go over the overall scheme in just a few seconds. But I guess I'd like to start off, right, with the title of the course. Right? We have Symmetry. And we will take advantage of the fact that I have multiple boards here and write Relativity. Well, of course, we are going to be dealing with special relativity in this course. Okay? Right. Now, when you saw the title of this course, you might have thought, why are these two stuck together in the same course? Because, do they actually have something to do with each other? Well, want to sort of just point out a couple things about the relationship there first. Well, let's first just define what a symmetry actually is. There are generally two components in any symmetry. There's going to be a transformation of some kind. Okay? And this can be things like, anything that kind of transforms the description of a system sometimes also transforms the system itself. So for instance, you can have things like, rotations in, let's just say three dimensions, kind of, 2 dimensions, 4 dimensions. After a while, you'll be, perfectly comfortable discussing rotations in 5 dimensions, I suppose. We also have translations. Okay, in other words, moving from one point to another. And we'll just say, to be more specific, we'll say that's in 3D as well. Okay, so that's one element, right? But not the only element, because that's just the transformation. The second element is the fact that you have a property right, which doesn't change with the transformation. Okay, and this could be, it could be just some, what do I have there? Okay, it could just be some sort of, number, right? Something that you calculate in before the transformation. You do the transformation, you get the same number back. It could also be just some other sort of feature, right? More generically, I haven't really defined what I mean by a feature. Perhaps a little bit more interesting for us is an equation or just some sort of relationship which does not change when you do the transformation, okay? So these two elements together basically describe a symmetry. Now, let's go to special relativity. What does this involve? Now, I think, you did this in CP1, right? You've learned special relativity, and you might be asking why is there more, right? Okay, well, let's go back to the postulates. Now, this is going to be sort of a somewhat more I don't remember exactly how you guys get presented with the postulates of special relativity. The first one should be familiar, which is simply that the laws of physics take the same mathematical form in all inertial frames of reference. Okay, now, you sort of know what an inertial frame of reference is. We'll get a little bit more more specific some other time, but we'll just depend upon the fact that you've actually had special relativity before, and we'll go with that for now. Okay, so that's the usual first postulate. The second one is oftentimes called the light speed postulate. So sometimes you will see this as, speed of light is constant in any frame. There's a somewhat more generic way of saying this. There is a finite maximum speed for what we will generically call signals. Okay. Now, the reason why I'm saying signals is because it's not necessarily light. Okay. It could actually be, just other things. Anything that is actually transferring information. So you can actually sort of, think about relativity in terms of just kind of like, available information at a particular time and space. Okay. So this is actually kind of useful, to just sort of generalize that concept. Now, how do we see the relationship between the two? Well, guess what? Both of these two statements, they are both statements of symmetry. Because, right, we said that there is a property, right? So here we have laws of physics, okay? And then we have the, which don't change. That's why they take on the same mathematical form. And then sort of implicitly, when we talk about what the transformation is, it's going between inertial frames of reference. Okay, so implicitly, when we say all inertial frames of reference, it means You can select one, you can transform it to another inertial frame of reference. The laws of physics remain the same. So we have both elements of symmetry involved here. Second one is also like that, right? Because, in the finite, the property then is the maximum speed of the signal, and this actually ends up being also, again, the same in all inertial frames of reference. So both of these statements are actually statements of symmetry. In fact, actually, I actually found this kind of useful when thinking about this again, just a couple days ago. Actually, phrases like this, and if you think about this in terms of just information, right? You almost wonder, and I suppose philosophers of physics probably have to deal with this bit. How can this be true without this being true? Is kind of interesting because if you didn't have this, then you have the possibility of sort of outrunning the signals, and the signals, after all, are what the sort of interactions that you're talking about in the laws of physics. That's what it is about. I mean, in some sense, the information that a body is someplace has to get out there somehow. Okay, and the question then is, can you actually outrun that kind of information? And what this says is that you can't outrun that information. Okay, sometimes this gets phrased, can you get punched in the face without actually seeing the fist coming for you? Okay. Anyway, that's kind of for the aspiring philosophers out there, you can kind of argue about that. There are a couple other different formulations of relativity, which one can get into, but we'll just sort of leave it in this form for now. Now, because of this, we're going to be. So these two topics definitely have something to do with each other, and we're going to be sort of taking it in that kind of order. So that's why then I have the sort of overall scheme for the lectures. So the first 2 weeks are sort of mathematical preliminaries, because we sort of have. Well, we're gonna talk about vectors. We're gonna talk about something called tensors. We have scalars, things like that. These are actually the things which actually transform. Okay, so when we talk about the properties, right, we're actually, the way that we describe the properties are oftentimes in the form of vectors and scalars and tensors and so forth and so on. Then we do the transformations, and that's actually where we get the groups, because what we do is that we form the transformations into groups, and we can then sort of talk a little bit about, basically, how the vectors and tensors transform, and also what can we say, what more can we say about those transformations, in fact. You do get some more out of that. Okay, but that'll actually be the first 2 weeks, and that's one problem set. Then I sort of have the second problem set being kind of week 3, which is, the first 2 weeks is pretty generic. Okay, I'm not actually sort of tying us to a particular way of looking at space and time. In fact, I don't think we even talk about time. We have one special little mention of it, but generally time is not really so much of a feature. That changes with the Lorentz transformations, because of course then we're starting to talk about Minkowski space, and we'll talk about the Lorentz group a little bit and the structure. Then after that we get into the mechanics. Sort of relativistic mechanics, and we'll see the sort of symmetries in operation. Electromagnetism actually turns out to be basically an exercise in relativity. Okay, and we'll see that for a couple weeks. And then finally, we kind of circle around and talk about radiation. Radiation seems like kind of a weird thing to tack on, but if you go back to this, right, it's one of the signals. Right? So after doing all the sort of physics of relativity, we get back, and in particular the sort of physical content of mechanics and electromagnetic fields and things like that, we sort of cycle back and realize that actually that propagating electromagnetic wave is potentially one of those signals. Of course, as I said, it's not the only one. You also have things like gravitational radiation, and more generically, you also have like gluon radiation. You don't see that much. Also, weak force and all that other kind of stuff. Okay, but we're not going to get that much into the, actually that's kind of like more like 4th year material and first-year graduate school material. Okay, but anyway, this is the start, right? You can look forward to that. Okay, right. I think that's kind of the outline. Right? Any questions for now? Yeah. Huh. No. Not yet. Right now, I mean, I am kind of taking a fairly generic kind of just sort of information perspective of it. Whether, kind of like potentially could you know that something has a certain property at a certain time? Okay, that's, I think about as far as I should go with that. You can probably, I mean, there are much more sort of deep discussions if you want to really get into that topic. Okay. Okay. Well, let's get into some of the meat. Right. So, symmetry and relativity. Okay. So let's do some definitions. All right. Where shall I start for definitions? Okay. Let's go here. Okay. Definition. What's a point? Okay. Now I know, if you go historically, Euclid did not define what a point is. Oh, actually, sorry. Euclid did define what a point is. It's in modern formulations of geometry where we say that this is an undefinable quantity, and I'm not going to improve on that. However, what we're going to do with this concept, I mean, it's more like we have an operational concept of a point, and there are actually sort of two concepts tied up in here. Okay, one is as a geometric concept. Okay? I mean, this is just basically a location. Okay? Sort of, it's, I'll say, it's a location independent of how the location is described. Okay? The second one is actually a set of n variables, which we will call coordinates. Okay? And yeah, so we'll write that as x1, x2, up to xn. Okay, now, that will look a little bit odd, the way that I've just written it. The superscript is just by convention. Okay, we will see subscripts a little bit later on. This is not an exponent, by the way. Okay, so it's not x squared or x cubed or whatever like that. I mean, if we need to take a, like a second power of x3, right, we'll actually write that as x3, put it in parentheses, like that. Okay, so it might get a tiny bit cumbersome, but it's not. Practically speaking, it's not that bad. Okay, now the coordinates. Now, when we have these two concepts here, right, there's a one-to-one correspondence between the geometric concept and the set of n variables. Okay, at least if these things are sort of, with an independent basis and all that kind of stuff. This is how we're going to use it. Yeah, okay. But, yeah, and actually this is, we do this in physics a fair amount where, well, actually, maybe not in physics. In physics, we actually, a lot of physicists get confused between these two things. Because operationally, it doesn't actually make that much difference, especially when you have a one-to-one correspondence. But mathematicians like making the distinction between sort of the abstract concept and then kind of a concrete manifest or a mathematical description of the concept. Okay, so you have the sort of like the abstract and then the description. And the thing is that you actually have multiple descriptions of the concept. Okay, so you can have things like Cartesian coordinates, you can have spherical coordinates. These are all different ways of basically describing a position, an abstract position. Okay, and yeah, and the reason why I'm sort of belaboring that just slightly is because, of course, it is the transformation between coordinates that we're going to be talking about when we start talking about symmetry. Okay, all right. Let's see. Right, okay, so the key point then, should write that down, is that transformations between coordinate systems don't change the geometry. Okay, though the coordinates can change. Right, okay, so now let's define what a coordinate transformation actually is. Let's see. So, coordinate transformation okay, we are going from, well, let's see. This is actually a set of n functions, of n independent functions, should be. Okay, and we'll label that, let's see, phi I, and we'll make it a function of all those coordinates. Okay, and right, you also, well, yeah, basically that is the definition. It's right. It is actually the set of functions, and just regarding the independence, it is sort of necessary and sufficient that the Jacobian, right? So you remember this kind of stuff from all that math that you've been learning. So you can do that. So the Jacobian is not 0. So, I mean, in general, you're also looking at an invertible transformation, right? So instead of, so going not, you can go from x to, well, we'll say the transformed coordinates are these. Okay, we'll write that with an x bar. So we can go from x to x bar. We can also go from x bar to x. Okay? Right. Now, this is a tiny bit pedantic. Oftentimes what you will see, instead of having to write all these phis, we actually just write these things as functions. So oftentimes you'll see written, and the way that I will actually do these things, we'll say xi bar, or x bar I, sorry, is x bar I function of x1, x2, etc. up to xn. Okay? And then when we talk about the inverse, I'll just slip this in here. We say that xi is equal to functions of x bar 1, x bar 2, etc. up to x bar n. Okay? Right, okay. So far, you're probably thinking, gosh, he's been belaboring that point, which is probably true. Okay, so in the next half, we're going to talk about, well, we're actually going to get a little bit more into what these transformations look like, but we are going to just have a tiny little break. So this is something I'm going to try to do, just sort of, halfway in between, because I know, you guys get tired writing stuff. So put down your pens, okay? Right. Now, yeah, how I tend to spend my time, as you mentioned, sort of, aside from thinking about symmetry and relativity. Well, no, actually, it's very difficult to get away from symmetry and relativity in what I do. I am actually a particle physicist like Professor Wilkinson. Well, not like Professor Wilkinson. It's kind of hard to be like Professor Wilkinson. But yeah, I tend to, we're working in the same field. Relativity is one of the sort of key features of the field. But I have a tendency actually I've been spending more of my time in dealing with collapsing stars and supernova, and in particular the neutrinos that come out of it. So just thought I'd show you some pictures. Now the reason why, these are just some nice little pictures that one gets, where you have a star, with a different structure. It sort of starts collapsing. You know kind of what the mechanism is, right? Because you sort of, burn up all the fuel. You can't actually maintain the pressure against gravity, so the star collapses, and then you get a shock wave. And sort of in the process of all that stuff, actually, in a core collapse supernova, probably about 99% of the energy is actually lost in the form of neutrinos. Okay, you don't see it, right? So even though this is like one of the brightest things that can light up the sky, actually the vast majority of the energy you don't see. We see it in underground detectors, which I'll talk about later. Okay. Now, the reason why this is actually kind of, or the reason why I left this in the first lecture, which is actually kind of more generically about symmetry, is that there's another use of symmetry, not just in terms of the general properties here. You've seen this before, where we like to sort of do dimensional reduction of a problem. So, well, we say, simulating a star in 3 dimensions is pretty difficult, okay? In fact, this is a picture of one of those simulations. It takes days or weeks, okay? There's a group in Germany which specializes in this kind of stuff, and you see this very, very turbulent flow within the supernova, which then kind of affects how, in fact, there's a big debate, well, kind of a debate on whether you can actually get these simulations to explode. First couple of times that they ran these simulations, the supernova really failed to ignite. Anyway, they think that they've kind of solved that one, as of about 6 months ago. This, as I said, this is complicated. So of course, one of the first things that people did was to reduce the whole thing and say, well, okay, actually, stars are kind of spherically symmetric, kind of. Right? So let's just do it as a one-dimensional problem, okay? One-dimensional problem's a lot simpler to solve. So here we're actually using spherical symmetry, okay? In other words, spherical symmetry means, you can rotate the system, right? That's the transformation. You rotate it, and things stay the same, okay? But in this particular case, it just turns out the approximation kind of works. It gets you a fair distance, but it doesn't get you all the details, okay? So oftentimes when we talk about symmetry, there's a lot of interesting physics in the violations of symmetry, okay? Anyway, as I said, and hopefully you did actually put your pens down, because this is clearly not on the syllabus for B2. Yeah, will not be, as I said, you will not be on the test. Just thought I'd kind of show it to you. I'll get into some of this stuff a little bit, as we go on through the course. Okay, now you can pick up your pens, and we can sort of keep on moving on with transformations. Okay. Right, you got a little bit of material to cover here. Right, so we had just generically transformations there. So let's look at an example of such a transformation. Okay, we're just going to look at, okay. So we'll use a vector example. Okay, right? So, a vector might, let's just say, in some coordinate system, okay, you have a set of points right, which we will call xi of t. So here, I mean, we are actually just talking about all of the, I mean, when I say xi, we are actually talking about all the coordinates, right? And now they're just going to be a function of some parameter, which we'll just happen to call t, okay? Right, so this defines a path. In the sort of, n-dimensional vector space, okay? And as I said, t is actually a real parameter. Well, I didn't say that, but it's what we call an affine parameter. So this defines this path along this curve. And let's say we want to calculate the tangent at this point, okay, or at any point along, for any value of t. We want to calculate the tangent here. So the tangent now is actually a vector, right? Now this is actually what we want to, well, let's see. Let's write that down. So we have a tangent vector. Okay, and that is simply going to be dxi dt. Okay, so here we have a vector, and we want to ask, if we go into another coordinate system, how does that look, right? So for instance, if you were to rotate a coordinate system, maybe better to use a different color. So let's say this is, this is your new coordinate system, just rotated. Okay. Now with the old, so here's your tangent vector. So before, these would have been the old coordinates. So let's see, old coordinates. And with this rotated, oh, that's kind of a pathetic right angle, but anyway. So now you have to do another projection here, and so this triangle gives you the new coordinates. Okay, so you're seeing that the coordinates definitely change, even though the vector is still supposed to be pointing in the same direction. Okay, so you want to find out what the relationship is there. Okay, well, this is relatively easy because you have all that wonderful calculus that you learned before. So we have dx bar I dt. Okay. We can just use the chain rule. So we'll go from j is equal to 1 to big N, and we have dx bar I, right? dxj, sorry, that then becomes a full derivative, dxj dt. Okay? Now, of course, I mean, this thing is probably, you've probably expressed it in terms of, the xi coordinates, right? So you have x1, x2, et cetera, xn. This, ultimately, you would like to rephrase in terms of x bar 1, x bar 2, et cetera, up to x bar n. Okay, so there is that little under the hood change of variables that you need to do as well. But the relationship between the the transformed vector and the old vector is this one, where you're just basically using the chain rule. Okay? Now, more generally speaking, right? So this is just an example of kind of like, well, a vector. Sometimes you'll not just have a vector. Sometimes you'll have a vector field. And I will write that as ai to the x, and here I'll just underline x to sort of to give that set of coordinates. And then the question is, how does this actually transform? And we can actually just, we're just going to take the analogy. Sorry, sometimes when people whisper, I wonder if I've written something incorrectly. Which is all right, please do correct me if I have. Okay? Anyway, okay. So we're going to, we can we can basically look at this and sort of by analogy, write down a transformation rule for the vector field. So we'll have a bar I, and this will be a function of the new coordinates, is equal to the sum j1 to n dx bar I dx j, and then a j. Okay, and these guys are functions of the old coordinates. Okay, so we are going to use this as our sort of transformation rule. Okay. And we can also, of course, do things like invert the transformation. So if we started off with this rule, we can, let's see, in order to invert, we multiply by dxk. Okay, so we'll just, first we'll do that multiplication. Still have the j here. So let's see, we have our x k, oh, right, x bar I, and then we had our x bar I, right, just copying from the formula now, a j, okay. And then, on top of that, right, this doesn't really help us that much because that's, we've just introduced another dummy variable. We will actually sum over I. Okay, so we'll add that in here as well. Okay, so basically, yeah, to invert, we're just adding that little part in front. Okay, now, of course, if you look at that sum right here, you're actually summing over the i's here. What that should give you then, when you do that sum, is just a Kronecker delta function. You have delta kj. And let's see, have I done anything wrong here? Yeah, I think that's all right. So in the end, what we should get is that a k is equal to sum I1 to n of dxk dx bar I, a bar I. Okay? So this is actually the, so this is it's the inverse of what you had above, but really it is actually just the same form because, as you see, all you've done is you've just switched the positions of all the unbarred and the barred quantities, okay? Now, going to introduce a term which will sound completely irrelevant. These are actually the transformation rules what we call contravariant components. Okay. We will have something to go with this. There's at least slightly a reason why it's called contravariant, but I'm just going to leave that definition there for now. Okay. Yeah. Let's see, which one? This one. Yeah. Okay, thank you for that. Okay, let's see. Right, now, yeah, as I mentioned, this is, I mentioned a contravariant. Now we're going to go for the other variety because not all vectors will, basically not all vectors will transform in this particular way. And the way that I'm going to illustrate that is to consider, maybe we'll start another board here. Okay. So we will now consider, instead of the x dt, we'll have sort of the gradient of a scalar function. So we have, this gives a set of n functions. Right? So that'll be d phi dx I. Okay. Right. Now, so it looks like, just like with the vector field, you have n functions, just, now in terms of the scalar field. So the question is, how does this actually transform? Transform to the sort of x bar coordinates. Okay. Again, we can just use our handy chain rule. So we have d phi dx bar I. Let me make sure of that. Right. Is equal to sum j is equal to 1 to n of d phi dx j times dx j dx bar I. Okay? Right. Now, how does this thing compare with what we wrote before? Now, unfortunately, I have it way on the other side of the room. Okay? But basically, let's see, we have it, yeah, I did the bars. So we're comparing with this guy. And the difference is in this derivative, right? That thing there looks like it is actually turned upside down. Now, of course, so this is actually just the inverse, except that you're still doing the same transformation from x to x bar. Okay? So you're still going from x to x bar, not the other way around, but you have the inverse derivative, partial derivative there. So let's try to, so basically what we have is that this set of functions is a different sort of vector. So and the terminology that we use for that is that we call this the transformation rule for covariant components. Okay? So just to summarize those transformation rules, if you have contravariant, then you have a bar I is equal to sum from j is equal to 1 to n x bar I x j a j. And you have covariant, which is, let's write this with, we will write with a subscript instead of the superscript. Sum from j is equal to 1 to n of dx j, right, dx bar I b j. Okay? Sorry? Yeah. Okay? Great. Okay. Sometimes, if you're wondering how to remember this, and I have to admit, sometimes I get a little bit imperfect about, I'll just sometimes forget and have to look this up again. When you're writing down these kinds of sums, just remember that for the contravariant one, you what I typically write, is actually the, what you're, you might say the index indicates where the destination coordinate system goes in your derivative. So if it's an upper index, you write it up on top, and if it's a lower index, right, you put x bar down in the bottom. Okay, so just in case that kind of helps for recollection. Okay, so let's now try so these are the transformation rules for the vectors. Let's try a combination of A and B. So let's do, say, sum of I1 is equal to 1 to n of AI and BI. Okay? Looks a little bit like a scalar product, doesn't it? Okay, and what we will do is that we will evaluate the transformed quantity. So A bar I. So let's say we do the transformation, and we have A bar I and B bar I. Okay, and we can just kind of like substitute in there. So you have the sum over I, and you have a sum over J. Okay, and that will be dx bar I dxj aj, sum over k, 1 to n, dx k dx bar I, and then b k here. Okay. Now, if you then do that other trick that you had before where you bring this sum into, do this sum first, now you have the contraction of these i's here, in which case you now have your delta kj again. Okay, you have your Kronecker delta. So that simplifies down to the sum, j is equal to 1 to n of aj bj. In other words, you did the transformation, and this is invariant. Okay, sometimes called a scalar invariant. So yeah, so we're already kind of seeing, if you're talking about symmetries and relativity, this is where this kind of thing will sort of pop in. You've done a transformation, and you have a property which remains the same. Now, another thing another reason this should look familiar is because, when you were doing sort of linear algebra, I think they introduced to you the concept of the dual space. You've seen this in linear algebra. You've also seen it in quantum mechanics. That's basically what is going on with the contravariant and covariant vector forms. Question? Oh, yeah, there should be. Yeah. Thank you for that. Am I missing? Okay, yeah, I think that's good. Okay, so yeah, so what we're seeing is that, if you have AI and A upper I and A lower I, those will be dual vectors. Okay? And that means that, in the context of linear spaces, there's a one-to-one correspondence between a vector and the dual space vector. And in fact, it's defined in terms of the scalar invariant. Okay? So, we could, as I said, we saw this in linear algebra. You saw it in quantum mechanics where you had sort of a ket, which, you could transform to a bra. So, in fact, we could write all this stuff in terms of kets and bras, but generally speaking, when we're talking about this kind of stuff, we generally don't use this kind of notation. We tend to use the component notation. Okay? Right. So, let's see. Okay. Labor-saving device, as we're getting close to the end. Actually, 2 labor-saving devices. Right. We're getting pretty tired of these things, right? Aren't you getting tired of these things? Yeah, okay. So we have something called the Einstein summation convention. Okay, and basically what we're going to do is that we're going to, what we notice actually is that the sums have a fairly regular pattern. Generally speaking, you have a repeated index. Okay, so the way that we write the transformation rule is with this, without the sum, and we're actually summing over repeated indices. should write down the rules here. Sorry. Okay, so it's a little bit more specific than that. Sum over an upper and a lower index. Okay, that means that if you had something like AI, you're not summing over that. Okay, so don't sum over that. I should be a little bit clearer here, though, because the differential okay, so d by dxi, actually this counts as covariant. Okay, which is, after all, I mean, so basically this, you know, if you have the derivative with respect to x with the upper index, that is actually a lower index, which of course is what you saw before when we were, when you were considering the gradient. Okay, that's, you know, in constructing or in coming up with the example for the covariant vector, this was kind of manifestly true. And then the other thing is you always sum over all the dimensions. Okay. Now later on, you know, we'll make a different. We'll actually distinguish between sort of space dimensions and sort of space-time. There will be a convention for that a little bit later on. But in any case, for now, this is our summation convention. And let's see, just cover one more labor-saving device. Okay, that was the summation convention. Now, transformation matrices. Okay, so we oftentimes will write, and you'll see this in the literature, you know, kind of a big lambda ij is equal to dx bar I dx j, okay? And so that enables you to write the transformation rule. Now, ai bar, got to remember all these bars, right? Lambda I j a j. Okay, so it looks a tiny bit simpler. Now, what does the covariant one look like? So that one we were looking for, so for the covariant version, we want AI bar is equal to dx j dx bar I a j. Okay, so this guy has got to be, you know, we'll write it just as sort of with a lambda tilde. And because this guy is upward and that one is lower, let's see, we still want to write that. Oh, gee whiz. That'll be ji. Okay, so therefore we can write, let's see, sorry, I've got to write that bigger. A bar I is equal to lambda tilde j I a j. Okay. Right. Okay. Now we sort of knew what the relationship was actually. I mean, you know, because we know what this this derivative is, and we know what the derivative is in the other case, you can pretty much write, and you know, you can work out the example with the scalar invariant as well. What you'll find is that this lambda tilde is basically lambda inverse. Okay, and in the lecture notes that I've been revising, in fact, I just went directly for the lambda inverse. Yeah. Okay, just one or two more little notes. Sometimes, well, because these are transformation matrices, you would like to write this in a matrix-like way, but the problem is that when you actually write it this way, these indices are not in the right place. Okay, so sometimes what you will see is AI bar is equal to AJ, and then here's your lambda tilde j I. Okay, that enables you then to, have the index that you're summing over be right next to each other, which is really how you like to do matrix multiplication. Okay, so sometimes we will see that. I think, actually, do I have any other notes on this? No, I think that's actually about it for now. Right, okay. So we have a couple labor-saving devices for writing down transformation rules. Yeah, so that actually completes the vector part. Tomorrow, we will, and that gives us the ability to start talking about transformations. Tomorrow, we'll start talking about the generalization of the vector, which is actually the tensor. Right, so any questions? Okay, maybe you'll have questions tomorrow. Yeah, so I'll see you then.